Hello. Well, thank you for coming, everyone, today, so we can talk about OpenXLA. The title of our talk is Unifying ML Infrastructure for Performance Across AI ML Frameworks and Hardware. I'm Paul. I'm an engineering manager at Google.
And I'm Nitin. I'm an engineering manager at Nvidia.
And unfortunately, Eugne isn't able to make it today. Cool. So the goal of OpenXLA is to defragment the ML compiler landscape. We want to be the open state-of-the-art ML compiler ecosystem that's built collaboratively with hardware and software partners. We use LLVM as a precedent here. We want to be very community-driven with our development and have neutral governance. And so you can see the role of the compiler illustrated on the slide is that you have a variety of frameworks for writing ML workloads, ML jobs, ML models, like TensorFlow, JAX, and PyTorch. And then you can easily target a variety of different hardware. So like x86 or ARM CPUs, Nvidia and AMD GPUs, Google TPUs, whatever other kind of accelerator that we expect. And we want to make it easy for model developers to get the best performance with hardware optionality and great usability. So you can try to model, you're testing it on a CPU. Once it's performing correctly, you can run it on a GPU, scale it up on a TPU or other kind of accelerator, whatever you want. So the challenges for the compiler is this is a classic MN problem, where there's M different front ends, and as soon as there's another great front end, you have M+1 different front ends, and then you have N back ends. And so if you just try to write all the code that goes between every front end, every back end, you're going to end up with inconsistent support. There's not a lot of portability, and you'll have a lot of missed optimizations. And these all inhibit innovation because there's going to be plenty of edge cases where an awesome feature that's just been added to the front end is only supported on one or two backends, and then if your favorite backend doesn't have it, then you have to support that feature. It slows everything down. So this makes it cost-intensive to build these end-to-end solutions, and OpenXLA's goal is we want to simplify and modularize this process. So that should improve the usability and code sharing. So the OpenXLA project, it's a ready-to-use end-to-end ML compiler stack. So at the core, we have the XLA compiler, which is a production-tested ML compiler for CPU, GPU, and accelerators. So this is used at Google for production jobs on CPU, also heavily on GPU increasingly this year, and of course the TPU side as well. It's used in both large-scale training and inference, and we'll have some benchmarks on slides later that highlight some of the progress that's been made on those angles. Using XLA enables model parallelism because you have automatic partitioning and a bunch of other features we'll talk about. It supports all the major frameworks that are very popular right now. So we have TensorFlow, PyTorch, and JAX support. One of the other components of OpenXLA is we've try to make it much more modular and composable. So at the very front end interface, we have stable HLO, which is the set of 100 very well documented ops, like convolution and matmuls, that you can construct an ML model out of. There's the XLA compiler in the middle, and we also have the pretty much just another runtime, PGRT, at the back end. And that interfaces with CPU, GPU, and TPU. This is all open source at github.com/OpenXLA. And you can check out the member organizations there that include Alibaba, Amazon, AMD, Apple, ARM, Intel, Meta, and Nvidia. So part of the motivating case for an ML compiler, this is a very simple vision of a component in an ML model. So this is basically just a simple gem operation where you're going to start off with a couple of weights that you want to multiply by some examples. Then you're going to add some biases. You're going to add a rectification linear unit to quash the outputs, and then perform a softmax to normalize for probabilities. This is a very common step that is a block inside of transformer models, repeated many times, and lots of ML models are built up hierarchically off of this kind of operation. Now, before you have an ML compiler here, the standard thing to do would be, okay, transfer your weights and examples to the GPU, which takes time, run a kernel, which executes quickly, and if it's smart, leaves the results on the GPU. Then you transfer the biases, which takes time, invoke a separate kernel to do the add, invoke a separate kernel to do the relu, and then add your labels and invoke another kernel to do the softmax. But all those activation overheads slows everything down, and you don't get peak performance, or you get very poor utilization on the hardware as well. So what OpenXLA provides is the compiler will process this entire graph at once. And what it will do is fuse all of these computations and avoid needing handwritten kernels for everything. It will fuse them all automatically into a single kernel that can be sent over to the GPU, invoked once, and you get the smallest amount of data transferred out. It can do some other optimizations, like it will propagate the layouts. So if a matmul knows that it's feeding into a convolution, it won't just materialize the outputs to look like a convolution. It can order the outputs the way the next operator expects them to be in a certain column fashion. And then it can also employ SPMD for single program multiple data to fuse it across multiple devices. The key components for OpenXLA, I already mentioned, so at the very top end, you have stable HLO, where HLO stands for high level offset. That's 100 operations that act as the input language for the compiler. They're very well documented in a separate repo under OpenXLA/stable HLO, which is a very good interface for people. And we're trying to make stable HLO heavily used, just even projects that are not the XLA compiler itself. It's a component of OpenXLA that we want broad adoption for. Then after it goes into XLA, there's several target-independent optimizations. So there'll be partitioning and distribution, so you can run the job on multiple devices, propagating layouts, handle scheduling for you optimally. So GPUs and TPUs, they have many kinds of memory that can be used to shard data or stage data of intermediate computations. And many of those passes can be reshared in the compiler between CPU, GPU, and TPU targets. And at the end, you have the hardware-specific backends that plug into. So CPU, just a couple to name here, CPU targets, GPU, TPU, Trainium, GraphCore, and there's even more inside the project. And I'll hand it over to Nitin.
Thanks, Paul. So we at Nvidia have been collaborating with Google on OpenXLA for LLM performance. And we have been working with different JAX frameworks. And XLA provides a large number of optimizations which transparently happen, and that sort of helps us obtain great performance. So XLA has GSPMD, which can automatically parallelize your computational graphs. It has something called a latency hiding scheduler. And for LLMs, there are lots of communications which happen because when you shard your model across a number of devices, you have to communicate between those devices in order to make sure that your computation can move forward. And XLA provides automatic ways to overlap these communications with computations, which is very key to improving performance. And with XLA, we also have specialized kernels for key operations, which are present in transformer-based LLMs, like the MHA. And we have specialized kernels that target specifically NVIDIA GPUs. So on the right side of this slide, we have a graph. So on y-axis, we have model teraflops per GPU for a GPT-3 vanilla 175 billion model. And on x-axis, we have put the performance that we saw for this particular model during the last year. And as you can see, in the last 1 year, we have obtained quite good performance improvements. And specifically on A100, we see about 2.5x increase, which is pretty good. Not shown on this graph are results on NVIDIA H100 GPUs, but we have measured them, and we see like an additional 2.2x increase if you just run with Hopper BF16. And we are also working with OpenXLA to accelerate support for FP8 on Hopper that is expected to provide more speedups for LLMs in general. For this particular benchmark, we also try to scale it across a large number of GPUs because that's what you want to do with LLMs. And we see that when we scale it up to 1,000 GPUs, we get very good scaling efficiency. showing that OpenXLA is really, really good for LLM performance. So I would encourage you to try it out on your GPUs. Over to you, Paul.
All right, thanks. And a couple other results that we wanted to excerpt here. So this is another interesting example from the Hugging Face blog called Faster Text Generation with TensorFlow and XLA. And in this demo, they have a collab to go through and some of the benchmarks that are listed there. But they start off using the Transformers NLP library in Python. And they just start off with using TensorFlow through tf.function, and then using kernel flow to execute the code. Then they also use PyTorch to run that. And then they, instead of using just plain TensorFlow, they use TensorFlow tf.function with JIT_compile equals true, which invokes the XLA compiler. And by just invoking the XLA compiler, they sped up that TensorFlow code 100x. That's the thing that's listed there. And they also got better performance than PyTorch in the examples that they run and the benchmarks that they ran. We did look into here that on the graph, if you look closely, so this is the lower is better, there is a little slight regression on the A100 because this specific graph here is on a T5 small model. But when you look at the results on the blog for a T5 large model, about with 3 billion parameters, then you see improvements with the A100 over the 3090 GPU. And one other example here is a blog from the PyTorch blog about Llama performance on PyTorch XLA. So they were using the Llama 65 billion parameter model. And in the context window, if I'm remembering correctly, it was 256 tokens for all of these runs. And what they did is measured the latency per token on the graph on the right side. So this is smaller is better. You want to lower latency. For the eager flow, and they're using Dynamo with Inductor as the compiler, and Dynamo with PyTorch XLA as the compiler. And in this example, you can see also that there were some places where Inductor outperformed PyTorch, but outperformed PyTorch XLA, but also some where PyTorch XLA outperformed Inductor. And so this is something that Google is investing in. We want to make sure we deliver the best performance with XLA on PyTorch and JAX and these key frameworks. And finally, this is for our call to action. The OpenXLA project. Our goal, to restate our goal, is to be an open, state-of-the-art, world-leading ML compiler. So the code is all available at github.com/OpenXLA. There's a couple mailing lists that people can check out for announcements and discussion. We have RFCs coming out somewhat regularly now. There's a Discord server for discussion where we have updates on the technical work that we're doing. We'll talk about the prototypes that we're building. And we also have community updates for people to dial into. There's a link to our next community update, which is coming in November, on top of a summit we have this week. And there's a link to our agendas there. Great. And thank you for your time.